In the last week lecture session, we had discussed about the first part of Chapter 4, Diode. For this session, I will continue the lecture with introducing several types of semiconductor diode which are available in the market and industry. As usual in our previous lecture session, there will be several parts of this lecture video where the students require to answer several quiz questions based on this lecture video and also as for the attendance. Okay, right, let's begin the lecture. Firstly, as usual, I will list down the learning outcome here for the Chapter 4. For today, there is one main outcome to be covered and achieved at the end of the lecture session by all of the students. Today all of the students are expected to explain the operation and characteristic of a Zener diode, Schottky diode, and Photodiode. The rest, which is from 4th until 7th's learning outcome, will be on the coming lecture session. In this part 2 of Chapter 4, we will discuss about the operational and characteristic of these three types of diodes from 4.4.1 till 4.4.3. From introducing each diode type, we will discuss and solve some example based on the related subtopic. To start the Zener diode, we can flash back the idea of breakdown region which has been discussed last week. VBR in the semiconductor diode is called as voltage breakdown, which indicate the reverse bias is taking place. But in the Zener diode, however, Zener diode is type of diode that is designed to work in the reverse breakdown region of its operating curve. Here VBR is noted as Vz. By referring the figure on the right-hand side, two things occurred when this reverse breakdown voltage is reached. The first is, diode's current is increased drastically. Secondly, the reverse voltage across the diode remains relatively constant. The Zener diode is mainly utilized as a constant DC voltage source. This region of unique characteristics is employed in the design of Zener diodes, which have the graphic symbol appearing in Fig 1.46a on your left. The semiconductor diode and the Zener diode are presented side by side in Figure 1.46 to ensure that the direction of conduction of each is clearly understood together with the required polarity of the applied voltage. For the semiconductor diode, the on state will support a current in the direction of the arrow in the symbol. For the Zener diode, the direction of conduction is opposite to that of the arrow in the symbol, as discussed in the page 4. Note also that the polarity of Vd and Vz are the same as would be obtained if each were a resistive element as shown in Figure 1.46c. OK, now, we will go in the Zener diode's application. On the left, when the V is larger than Vz, the on state is activated and the Vz is constant. However, on the right blue box, when the V is less than Vz, the off state is activated, which will noted as open circuit. So now, we can understand that the voltage given to the Zener diode plays an important role for activating it into the on state. Four main characteristics of Zener diode will be explained by using the figure on the right side. IZK, or the Zener knee current, is the minimum Zener current which is essential to keep the diode operating in the breakdown region. At or near IZK, the Zener voltage is less than the nominal Zener voltage Vz. The nominal term here is simply indicates that it is a typical average value of Zener voltage. IZT, or Zener test current, is corresponded to the rated Vz, while Vizm is the max Zener current, is the current which may not be exceeded. The specification sheet for a 10 volt, 500 mW, 20% Zener diode is provided in this table. Since this is a 20% diode, the Zener potential of the unit 1 picks out of a lot, a term used to describe a package of diodes, can be expected to vary as 10 volt 20%, or from 8 volt to 12 volt. Both 10% and 50% diodes are also readily available. The test current IZT is the current defined by the 1/4 power level. It is the current that will define the dynamic resistance ZZT and appears in the general equation for the power rating of the device. That is, PZ max equal to 4 IZT multiply with Vz. Substituting IZT into this equation with the nominal Zener voltage results in will be 500 mW. The Zener potential of a Zener diode is very sensitive to the temperature of operation. The temperature coefficient can be used to find the change in Zener potential due to a change in temperature using the following equation, where T1 is the new temperature level. T0 is room temperature in an enclosed cabinet 25 degrees Celsius. Tc is the temperature coefficient and Vz is the nominal Zener potential at 25 degrees Celsius. In order to demonstrate the effect of the temperature coefficient on the Zener potential, consider the following example. The example is to analyze the 10V Zener diode described by given table if the temperature is increased to 100 degrees Celsius, where this is the boiling point of water. Substituting all given value into EQ in page 9, we obtain delta Vz is 0.54 volt. The resulting Zener potential is 10.54 volt. It is important to realize that in this case the temperature coefficient was positive. For Zener diodes with Zener potentials less than 5 volt, it is very common to see negative temperature coefficients, where the Zener voltage drops with an increase in temperature. Figure on the right-hand side provides a plot of T versus Zener current for 3 different levels of diodes. Note that the 3.6 volt diode has a negative temperature coefficient, whereas the others have positive values. Okay, so far, how was the understanding of the Zener diode? I hope you guys are okay and get the idea of this sub-chapter. Now, we will go into the application with Zener diode. Voltage regulator. Have you heard about regulator before? Voltage regulator is a circuit which was designed to maintain a constant voltage despite anticipated or predicted variations in load current or input voltage. This voltage regulator performs two functions, which are to reduce the ripple or variations in the output voltage and to ensure that the DC output voltage from the power supply will remain relatively constant despite variations in load current demand. Speaking of the voltage regulator, there are two types of analysis which related to the voltage regulator. Voltage regulator with no load and with load. First, the voltage regulator with no load given. We can make an assumption of the VI is varying from VI minimum and VI maximum. For positive applied voltages less than the Zener potential of 20 volt as example here the Zener diode will be in its approximate open circuit state, and the input signal will simply distribute itself across the elements, with the majority going to the system because it has such a high resistance level. For the negative region of the applied signal the silicon diode is reverse biased and presents an open circuit to the series combination of elements. The result is that the full negatively applied signal will appear across the open circuited diode and the negative voltage across the system locked in at 0 volt. The analysis for voltage regulator with load is first for fixed quantities and then followed by a fixed supply voltage and a variable load. For the first case, both voltage and load are fixed. Step 1 is checking the state of the Zener diode by removing it from the network and then calculate the voltage across the resulting open circuit. Substitute figure 2.112 to figure 2.113 is for understanding the equation. Here V is parallel to VL. So, V is equal to VL. This V is referred to this voltage divider. There are two conditions of V compared to Vz which will describe the on or off state of Zener diode. For the V is greater than Vz on state is activated while when the V is less than Vz will be off state. For the step 2, substitute the appropriate equivalent circuit and solve for the desired unknowns. Here, we will use the KCL as to describe the current flows. Based on the Ohm's law IL is equal to VL by RL. On the other hand, IR is VR by R. Here VR is the difference of voltage between VI source and VL. Therefore, we will have PZ is IZ multiply VZ. For the second type of the voltage regulator which is with fixed source and varies on the load. To determine the minimum load resistance of Fig 2.112 on page 42 that will turn the Zener diode on, simply calculate the value of RL that will result in a load voltage VL is equal to VZ. Solving for RL from here, we will have equation 2.20. Any load resistance value greater than the RL obtained from equation 2.20 will ensure that the Zener diode is in the on state and the diode can be replaced by its VZ source equivalent. The condition defined by equation 2.20 establishes the minimum RL, but in turn specifies the maximum IL in next step. Next step is to find the IL, which is VL by RL or RL min. Once the diode is in the on state, the voltage across R remains fixed at R is equal to I minus and IR remains fixed at VR by R. Then, we need to understand the Zener current. IZ is IR minus IL. This will be resulting a minimum IZ when IL is a maximum and a maximum IZ when IL is a minimum value, since IR is constant. Since IZ is limited to IZM as provided on the data sheet, it does affect the range of RL and therefore IL. Step 4. Substituting IZM for IZ establishes the minimum IL as IR minus IZM. Here the maximum load resistance is Vz by IL min as in equation 2.23. Now we can conclude that, due to the offset voltage Vz, there is a specific range of resistor values and therefore load current that will ensure that the Zener is in the on state. Too small a load resistance RL will result in a voltage VL across the load resistor less than Vz, and the Zener device will be in the off state. Next we will take a look at examples for these two cases of voltage regulator. For the case number 1, we need to find the VL, VR, IZ, and PZ from the figure given here. And then second task for this example is to repeat the analysis with a different RL, which is 3 kΩ. As discussed earlier, at first, we need to determine V from the figure on the top left, whereby we have an open circuit in the middle. Here V is equal to VL and we will have 8.73 volt. Since the 8.73 volt is less than 10 volts, this diode is in the off state. As mentioned in the question, we need to find VR, IZ, and PZ instead of only finding the VL. VR is the difference VI with VL. Here we have 7.27 volts. As the diode is in off state, current is not flowing and the IZ is 0 ampere. Power over here also will be 0 watt as the zero current available here. By changing the RL from 1.2 kΩ to 3 kΩ, we will find the all elements VL, VZ, IZ, and PZ. VL here is 12 volts. Since V equals 12 volts is greater than Vz, which is 10 volts, now the diode is in the on state. Therefore, the Vz now is 10 volts. Calculating the VR gives us a 6 volts. To calculate IZ, we need to use the KCL as IZ equal to the substation of IL from IR. IZ here is 2.67 mA after we find the IR and IL one by one. The power is Vz multiply with IZ is equal to 26.7 milliwatts. For the case number 2, we need to determine maximum wattage by using RL and IL, which will result in VRL being maintained at 10 volts. To determine the value of RL that will turn the Zener diode on, apply equation 2.20 on page 44, we will have RL equal to 250 ohms. The voltage across the resistor R is then determined by equals I minus as on page 45, as 40 volts. Then the magnitude of IR is equal to 40 mA. As the minimum level of IL minimum in equation 2.22, IL minimum now will be 8 mA. And the maximum value of RL now is 1.25 kilo-ohm. A plot of VL versus RL appears in figure 2.120A and for VL versus IL in figure 2.120B. Finally, the power is 320 milliwatts by multiplying the 10 volts with 32 milliampere. Now we will jump into the next sub-chapter, which is about Schottky diode. Schottky diode is also known as surface barrier diode or hot carrier diode. The diode symbol is illustrated by this figure on the right-hand side. Here is the list of Schottky diode's applications. Speaking of Schottky diode, firstly how it was made. Basically, it is a construction of a metal semiconductor of normally N-type silicon junction. Host of different metals such as molybdenum, platinum, chrome, or tungsten are used. Here, different construction gives different characteristics, such as by increasing frequency range, lowering forward bias, and increasing the level of ruggedness. In both material, electron is the majority carrier. When both N-type and metal are joined, electrons in N-type silicon immediately flow into the adjoining metal, establishing heavy flow of electrons. The electrons from N-type material are called hot carriers due to having very high kinetic energy compared to electron in metal. This heavy flow of electrons into metal creates a region near the junction surface similar to depletion region on p-n junction diode, which has been discussed before. Additional carriers in metal establish a negative wall in the metal at the boundary between these two materials. This will result surface barrier, which is created at the between two materials and preventing any further current. The barrier at the junction for a Schottky diode is less than the p-n junction diode in both forward and reverse bias regions as in this figure. The Schottky diode equivalent circuit is presented as in the top figure, and the approximate equivalent circuit as the bottom figure. The third type of semiconductor diode for today's lecture session is photodiode. A photodiode is a semiconductor device that converts light into an electrical current. The current is generated when photons are absorbed in the photodiode. The common, traditional solar cell is used to generate electric solar power is a large area photodiode. Photodiode is built by a semiconductor p-n junction device which operation region is limited to the reverse bias region. Basic biasing arrangement in this photodiode is the light is applied to the junction, and usually, the lens in photodiode here are used to concentrate the light to the junction. The graph shows that the current will only return to zero when positive bias equal to Vt is applied. There are two applications which commonly utilize the photodiode. First is the alarm system. The reverse current will continue to flow while the light beam is not broken. If someone or something are crossing the door and the light beam is interrupted, the reverse current drops to the dark level and sound the alarm. The second application for this photodiode is the counter operation system. The reverse current will continue to flow while the light beam is not broken. As each item passed, the light beam is broken and reverse current drops to the dark level. Each time the current drops to dark level, the counter is increased by 1. With that, I end my lecture for this chapter 4 part 2 about the diode. I hope that you all gained knowledge and ideas this chapter. If you have any question, please contact me at nickzarifi@utem.edu.my.
Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.